Hello, everybody. This is a video reintroducing Newton's law of gravity and how it relates to potential and kinetic energy. What Newton theorized was a mathematical expression that described the force between two masses. There might be something in this equation that is new for you. If you have a radius from this mass to this mass, a radius r, it is actually a vector. Some call it r hat. But the r vector is positive coming out of the mass by convention. So it's not like X, Y, and Z where you can kind of choose. R is kind of already determined to be positive from this mass to this mass. So yes, we're choosing a mass. Obviously, if we choose this mass, it'll go the other direction, but we're choosing a mass to be the center, to be the reference frame, and that'll be the big M. And if that's the case, then obviously the force will point inward. This is an attractive force, which means it's negative. So all this means is that it goes against R. R is outward. And all this means is attractive. You do not need to know really any of that. I'm just explaining why this negative sign is there. It means attractive. So it doesn't mean left, it doesn't mean right, it doesn't mean up, it doesn't mean down. It means attractive. In this case, it means right. If I redrew the masses opposite, it would mean left, right? It means attractive. It means inward. Opposite the outward radius. So radius is like spokes of a bicycle wheel. The force goes opposite to them. I hope that actually makes sense. I hope that actually helps make this equation mean something more physically real. Not something necessarily to memorize, it's something to visualize, that this is always inward, always attractive. It depends on the two masses and, of course, the inverse square of the distance between them. So if I were to graph it, force versus radius, it would be like this. Negative meaning attractive, inverse square law. That's it. Cool. So that's step one. Of course, little g is important. Sorry, big G is important. Big G is the gravitational constant, universal gravitational constant, and it's that many in MKS system units. Great. So what I want to do is kind of instantly go to the next step. That we have a force, great. Right? I'm assuming we've dealt with forces. We can figure that out. Great. There's a lot we want to talk about. And here's where I want to go with this. So, yeah, potential energy. Before we derive a formula for potential energy, I want to do a little thought experiment. So from this equation, we can clearly solve for little g. We can solve for the acceleration by setting Fg equal to ma. We call a the acceleration of gravity. If gravity is the only force acting, we can replace this with g. And we set gmm over r squared equal to mg. I'm just doing absolute values here just to get the magnitude, because obviously we know this is attractive. This will be inward in direction. So I'm just doing magnitude values here. And gmm over r squared equals mg. We can cancel that. We did this in class, and we get gm over r squared is the acceleration, which doesn't depend on the mass that's falling. It just depends on the distance away. So if this is r away from a little mass m, I'm sorry, from a big mass m, the little mass will fall at an acceleration of g, which now depends on the inverse of r squared. Great. So as it goes closer, what happens? Well, let's see if I can squeeze this in here. As r decreases, g clearly increases. G goes as 1 over r squared. It's a 1 over r squared proportion. So if I have half the distance, that means, sorry, half. That means 4 times the acceleration. As it gets closer, it goes faster and faster. I should say it accelerates faster and faster. And of course, if it's falling, it's going to be moving faster and faster, but it's going to be moving faster at a faster rate. As it goes closer, it's like the force increases dramatically. So this is an increases in the negative direction. So whenever we look at graphs, ah, whenever we look at graphs, we want to look at the magnitude of the graph. So this is an increase. This is bigger than this, which is bigger than this, which is bigger than this, which is bigger than this. So this is an increase of force, an increase. As r gets smaller, force gets bigger inward. The negative just is a direction because this is a vector. So all of that's really important. So now we can go back to how does this relate to potential energy? So before we actually calculate and derive the formula for potential energy, notice we're kind of revisiting all of these things that you guys kind of sort of worked on, maybe took for granted or simplified. We're going really into the nitty-gritty details. Let's do a thought experiment. Simple thought experiment. Don't overthink it. Cool. I have 2 masses and I drop this mass. And let's say this mass starts R naught. We'll do naught for initial. R naught is initial position, initial distance, initial radius, however you want to look at it. And V naught is initial velocity. Some of you might have done V initial for that, or R initial with an I. I prefer the naught. It's easier for me to see and easy for me to write. It's like time equals 0. It's the starting place. So R naught, let's have it be huge. Let's have it be very far. Relatively very far, which means like it's essentially at infinity. Obviously, it can't ever be at infinity. There's still a physical interaction. So there's still a tiny, 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 tiny force acting on this, therefore resulting in a tiny, 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 tiny acceleration that we can calculate if we know the actual distance. But as r goes to infinity, the force goes to 0, gravity goes to 0, but it never actually gets there. It never actually is 0. No matter where these are in the universe, galaxies 13.7 billion light years away are interacting with my body right now. Just so tiny, it's essentially 0. It's very far. It's essentially no interaction, but it's more than 0, which means that if I had enough time, if I had trillions of years, this would eventually fall toward this mass. Eventually, if there's nothing else in the universe, these will eventually come together and collide. I want to know what happens to all of these values. What happens to velocity? What happens to force? What happens to acceleration? And most importantly, ready for this? What happens to potential energy and what happens to kinetic energy as it moves, or I'll even use the word as it falls, because it's falling toward this mass. This is our center of mass. We'll keep this one fixed. Yes, they will fall toward each other, but we'll be in the reference frame of this mass. Again, we've chosen this as our reference frame. The big M, I will choose as the reference frame. It's arbitrary, but I'm just going to fix that for simplicity or for clarity, really. We're not oversimplifying. We have to choose a reference frame, so I'm choosing that one. So as it falls, what happens? Well, V clearly increases, but why? Here's why. Because the velocity is to the right, and of course the force is to the right. And we know if those align, then that's speed up. Great. Force does what? Well, because R is decreasing, and force is increasing because force goes as 1 over R squared. That's the reasoning. Notice I'm doing this in shorthand. It'd be probably nice to write it out as a sentence, but the force increases because the radius decreases. Great. Acceleration, same as force, because those are the same thing. Those are the exact same thing. And by the way, the reason why this is the only thing is because only gravity is happening. There's no other forces at play. So we're just isolating gravity. So the force is gravity. Because of F equals ma, if you guys remember, really important, whatever F does, A does. These are always the same thing. Conceptually, these are always the same thing. If force increases, acceleration increases. If force flips direction, acceleration flips direction. Right? F equals ma says that they are exactly the same thing conceptually, and as a vector, they're just different mathematically by mass. Mass determines their exact values, or should I say the exact value of A specifically, because F is determined by the gravity equation. F is determined by this. A is determined by this. But as a vector, they are in the same exact direction, orientation, and pattern. Great. All right, now, ready? What happens to potential and kinetic energy? Kinetic energy first. That's obvious. V increases, so kinetic energy increases. 1/2 mv squared. So V goes up, so KE goes up. Great. But if KE goes up, I know that delta PE equals negative delta KE. That's true everywhere. That's just a universal truth, right? This is one of those foundational principles that exists no matter what question you're doing. And that's why I love this. The energy theory, energy conservation, transfer of potential and kinetic, that applies to everything in existence. That's why we're starting there. So let's apply this. Well, clearly, if kinetic energy goes up, potential energy goes down. Potential energy goes down as something falls. And you can just do a simple thought experiment. I'm going to drop this pen. If I drop it, potential energy decreases, kinetic energy increases. I'm converting potential energy into kinetic energy. Done. Great. So we've conceptually mapped. I call this a map. When I say map, I don't necessarily mean like a geographic map. I mean like a conceptual map. Like you're laying out a logical outline of here's what is happening to all of these things and why. We want to connect the equation to the picture and the concept, and I think this is how it could look. If this is as concise as possible. This is as concise but complete. So it can look like this. It can look like complete sentences as long as it's not lacking any information. So concise doesn't mean shortcutting information. Concise just means this is exactly what's happening and exactly why. So we're not shortcutting any information. Notice we're including every piece of information here, every connection. Done. Great. Cool. So ready for the kicker? Ready for the whatever, the big moment? What was the initial? Wait, ready? So sorry, let me do new page. I have this mass falling toward this mass, tiny little force. V increases, kinetic energy increases. So I have V, V, V. I have force, force, force. This doesn't, they don't always correspond, but in this case they do. Something falling is going to increase its force because Fg goes as 1 over r squared. Velocity increases because the acceleration points in the same direction as the velocity. That's why the velocity increases. Here's why the force increases. Those are two completely separate things, but they are both increasing. So know your logic, right? But here's the whole point. I probably shouldn't have cluttered my diagram, right? So here I have some initial potential energy and I have some final potential energy. Here I have some initial kinetic energy and some final kinetic energy. And the most important equation we're going to use in this first unit, the most important equation we're going to use, is this. That initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy. We have conservation of energy. That E initial equals E final. Energy is conserved. This is the most important equation we're going to use all the next couple weeks. We're going to plug in numbers to this. We're going to use it to solve for different things, and we're going to draw diagrams that show why this is interesting and why this works. That's a summary of the next couple of weeks. So how does it apply conceptually? We don't have an equation for these yet, but we can think about the pattern first, which I think is really important and useful to think about the pattern first, because then the equation will then make tons more sense. What is the initial kinetic energy? Well, let's say that I dropped it. Let's say that this was dropped. Dropped means you just let it go. I just dropped this pen. What's its initial velocity? 0. I didn't throw it. I didn't launch it from a cannon, right? I just let it go. When you let it go, I didn't give it any initial force, any initial velocity. So the initial kinetic energy, of course, is 0. The final kinetic energy is large, whatever 1/2 mv final squared is. And honestly, that'll usually be the unknown that we will solve for, but we know it's a big value because it's speeding up this whole time. We know, therefore, that this is opposite large. This is negative large or very small. And remember, I want to be careful here. I want to go back to here where I said for force, more negative means increase because it's a vector. If I have a more negative versus a more positive, that's a bigger vector. Pause and let that make sense. This is a greater vector. It's a larger vector in the negative direction. Because remember, negative just means a flipped direction. It means inward in this case. Whereas here, we're dealing with energy. So energy, if I say smaller, could be more negative. And I'm so sorry if that confuses your brain, but we want to unconfuse that and just say it as it is. I'm not going to shortcut and I'm not going to try to I'm going to help us. And I'm here to help. That we have a scalar. This is not a vector. It doesn't have a direction. Energy doesn't have a direction. So when it gets smaller, it can get more negative. So a more negative vector is bigger in magnitude. And I'm asking you guys to learn this physics. This is the physical meaning of these numbers. A vector that's more negative is bigger in magnitude because the negative doesn't mean negative. The negative means direction. But for a scalar, the negative means more negative. It means like I've subtracted a value. I've decreased it. This has decreased. And if you need to go over that over and over again until it makes sense, it'll make sense. It'll click. That this is the important difference between a scalar and a vector. They're completely different things. So the question is, what was the initial potential energy? Because then that'll help us determine, well, if it's decreasing, where did it end up? Well, here's the thing. Do you guys remember what potential energy is? It's interaction energy. So when R is near infinity, the force is near zero, which means the interaction is at zero. Which means the interaction energy is zero. Yeah. If that just clicked, you're on it. If that's going to take a moment, rewind that. But that's the logic. And that's why we need to define potential energy as the energy of an interaction. Am I interacting with like the Whirlpool galaxy 100 million light years away? Yes, I am. But what's the interaction energy there? Well, it's going to be barely nothing. It's not hugely positive. It's not like some huge positive value where there's a lot of interaction. There's a very little potential for interaction, very tiny potential, because the distance is so far away. So please don't go to any equation you might have learned in the past. Go to the pure concept of the word potential. If you go to that word potential, I think it's clearly obvious that the potential of me interacting with the Whirlpool galaxy is basically zero. It's asymptoted. It's asymptoted to zero. It is not zero because clearly gravity transcends infinitely far through space, which is crazy in and of itself. But the interaction is zero, which means the interaction energy is zero. So if I've subtracted from zero, that means the final potential energy is negative. I have a negative potential energy. In fact, all potential energy of gravity is negative for this reason. Because if I apply this to any circumstance, this applies to any circumstance, the only time that it's zero, which it never is, it approaches zero as R approaches infinity, because then the interaction, and I like writing it in big caps, interaction, goes to zero. But it never actually reaches zero. There's always some interaction. But the interaction is negative, which, by the way, relates to the fact that this is an attractive force. If you have a negative potential energy, that's an attraction, which we can prove eventually. And this is called a binding energy. This is one of the most important concepts in physics. That a negative potential energy, whether it's gravity, whether it's electricity, whether it's strong force, whether it's a spring, any force in the universe, if it has a negative potential energy, it's an attraction. That means two things are bound together. If it's positive, it means repulsion, or that things are being pushed away. They're not bound, they're repelling. So a negative potential energy is binding. And yes, gravity is always negative by this logic. And again, rewind this. I've started out with zero and I've subtracted. So I have to be negative, right? What's the logic? I'll rewrite it here. Initial was zero. and PE decreased that are essentially really, really far away. Call it, I say prox, that's not mathematically correct, but you get the concept. R really far away. As P decreases, as R increases, PE decreases because kinetic energy increases. That's the Y. Because of the force alignment with the velocity, because of this, right? So see the logical progression. Force is attractive, so it speeds it up. So KE goes up, so PE goes down, but it went down from zero, so it's negative. This is going to be cool. I'm learning this. Wait, I got it. No, not that one. Oh, sorry, guys. I'm trying to figure out how to exit whiteboard. It's not exiting. I want to go back. I'll do it. Stay with me. It's new to me. I wanna see you face to face. Did I do it? I did it. Yes. But that's it. I hope that made sense. That is, believe it or not, step one. So notice the intricacies there of all the connections. We want to go through those and just be really good at connecting those dots because in doing so, we can actually derive the real equation for potential energy. MGH is not the equation for potential energy. That is assuming a few things that are greatly restrictive in the way that that formula can sort of actually work. That in the grand scheme of the universe, the grand scheme of any given situation, it's very limited. So we want to have a more universal equation that we can use that confirms the concept we just said. Feel free to pause, go back, watch everything. I'm going to do another video. We're going to derive that equation next. Bye, guys.